Hawking radiation. The fuse, Hawking radiation as a clock. Here S where the whisper turns into a ticking sound you can't unhear. If those compact lenses are primordial black holes, they aren't inert. They're leaking. Not like a cracked pipe, more like a faint, relentless hiss from the edge of space-time. Stephen Hawking showed that when you mix gravity, quantum fields, and a horizon, you don't get silence. You get a temperature and a clock. Stakes first. Big black holes are cold. Small black holes are hot. That simple flip has teeth. It means every black hole, no matter how old or quiet, is a timer. The smaller it is, the faster the digits fall. If the dark is full of small ones, then the universe is full of clocks we never set and can't stop. To understand the clock face, you need one relationship. Temperature is inversely proportional to mass. Double the mass, halve the temperature. Shrink the mass and the temperature rises. Radiation steals energy. Energy is mass. The hole loses mass, gets hotter, radiates more, loses mass faster. That curve is the fuse. Mass up, time up. Mass down, time screams. Action. People who live in equations translate this into lifetimes. A primordial black hole with the mass of a mountain, call it 10-15 grams, lasts roughly the age of the universe. A bit heavier and it will outlive galaxies. A bit lighter and it's already gone, having evaporated in a fierce finale long before stars ever formed. That's why the mass window in Chapter 2 mattered. Survive today and you're heavy enough to still be here. Fall below that threshold and you die young with a flash. Micro-stories make it real. A pebble-mass black hole, ridiculously tiny by astrophysical standards, would be gone before you blink. Less than a trillionth of a second and it would vaporize, unloading its stored energy in a spray of particles. A mountain mass one is different. Colder, patient, lingering across cosmic eras like a coal that refuses to go out. Same physics, different pace. Meanwhile, the spectrum of what comes out shifts with time. Early on, when the hole is heavier, it emits mostly low-energy photons and a trickle of light particles. As mass drops and temperature rises, higher-energy quanta join the party. Electrons, muons, eventually quarks and gluons that hadronize into jets. The closer you get to the end, the harder and brighter the spectrum. The fuse doesn't burn evenly, it flares at the end. Complication. We're still playing a semi-classical game. We use quantum fields on a smooth space-time background to get the radiation. That's good enough until it is. Near the final moments when the hole shrinks to scales where quantum gravity should speak, our math stutters. Do you get a runaway fireball, a burst of gamma rays with characteristic structure, a Planck mass relic left behind? Each answer writes a different ending on the universe's ledger. This is theory space. Credible possibilities, not settled facts. Impact. Once you accept Hawking's clock, PBHs become more than dark matter candidates. They're time-stamped artifacts. Find one in the right mass range and you can predict, not perfectly but meaningfully, how much time is left on its fuse. The late-stage surge isn't just fireworks, it's agency. It can heat, ionize, seed particle cascades, and this is the part we'll come back to, dump concentrated energy into a small region of space at energies our universe rarely accesses anymore. What nobody knew at the time the idea first landed was how human that clock would feel. In a late-night meeting, someone asked, if there's one within a few hundred light years that's small enough to pop in the next million years, would we know? The room paused. The honest answer, probably not until the last seconds unless we're watching hard in the right band. The hiss is subtle. The final breath is not. There's a quiet irony here. The very constraints that carve out the allowed mass window also define the tempo. Too light, and PBHs would have shouted in gamma rays long ago. Too heavy, and they're essentially eternal, cold, and silent on human timescales. The band that survives is the band where the fuse is long but not infinite, the radiation faint but not absent, the finale distant but guaranteed, given enough time. Meanwhile, there's another thread tied to the clock: information. If evaporation is real and complete, what happens to the information about what fell in? The page time, the moment when half the information has effectively come back out in correlations, arrives earlier for smaller black holes. That means small PBHs cross the line where the emitted radiation carries structured entanglement relatively quickly. The hiss isn't pure noise anymore. It could be tangled with the hole's interior state in ways we're still trying to decode. Here's where the stakes sharpen. Late evaporation couples the interior's deepest secrets to the outgoing quanta. If anything about the black hole's birth environment or internal microstate can imprint on that radiation, the end stage isn't just an energy event, it's a message event. If there's any message to read, that's a big if, and we'll handle it when we get to horizons as switchboards. For now, keep the clock in mind. Human moment, a whiteboard in a cramped office, markers running dry. A student draws a simple axis, mass on one side, lifetime on the other, curving up steeply. She dots a point where the allowed PBH band sits. Her advisor draws a small flame at the low mass end and says, "Everything over here is already ash. Everything over there is stone cold." He taps the dot. These are the embers. And one more complication we can't dodge, the runaway finale. The last seconds aren't just hotter, they're faster. The mass loss rate spikes, the spectrum hardens. If a PBH dies within our cosmic neighborhood, it could write itself into our sky with a burst we'd see across observatories. We've listened for those hawking pops. So far, silence. But silence is only a statement about now. This is the moment everything changes in how we think about time. With PBHs, the universe seeded clocks into its own fabric. We didn't wind them, but we live under their schedule. And their last breath might do more than light up detectors. Under the wrong conditions, it could nudge the vacuum itself. To understand why that finale is dangerous, we need the aftertaste of energy. We need to look at what a last exhale can trigger. The final second, runaway evaporation. It doesn't announce itself with a drum roll. The final second begins like any other second in the black hole's long life, hotter than a moment before, colder than a moment after. But the slope is different now. The mass is falling off a cliff. Temperature rockets. The quiet hiss hardens into a torrent. What used to be a gentle trickle of low-energy photons becomes a storm front of particles slamming outward from a shrinking horizon. Stakes first, because they're not abstract. End-stage evaporation concentrates unimaginable power into a volume that's vanishing. The smaller the hole, the tighter the focus. That means the energy density, the punch per cubic centimeter, spikes to levels the universe hasn't casually produced since its first fractions of a second. Space near the horizon becomes a furnace where quanta are born already sprinting. If one of these pops close enough, it could draw a line across our sky in high-energy light, a signature nobody could wave away. Action as it unfolded in the equations and the imaginations of people who trust them. As the temperature climbs, the spectrum hardens. First more energetic photons, then electrons and positrons arrive in force. Muons, taus, neutrinos, gluons. If the temperature clears the QCD scale, quarks and gluons spray out and immediately hadronize, fragmenting into jets of pions and other mesons that decay into gamma rays and neutrinos. It's not a single flash. It's a brief, chaotic shower where the whole acts like a collider with no engineering limits and no safety rails. The horizon shrinks between emissions, and with each tick the next emission is hotter and quicker. The cadence accelerates. Blink, flare, scream. Meanwhile, detectors wait. Ground-based gamma observatories stare at large patches of sky, looking for the telltale rise of a hard spectrum followed by a sudden cutoff. Space telescopes comb archival data for unassociated bursts that don't fit the usual gamma-ray burst families. A few claims have flirted with the idea, events that seem too short, too hard, too lonely, but nothing has survived the gauntlet of scrutiny. For now, there's only the expectation. When one goes, we'll know. Until then, silence. Complication hits right where the curve gets steep. Our math is semi-classical, and it's at its bravest when the hole is still large enough that spacetime looks smooth. In the last instance, the horizon shrinks to scales where quantum gravity shouldn't be a footnote anymore. Does a firewall form, tearing up the story we tell about smooth horizons? Do new channels open that bleed energy into hidden sectors? Does evaporation halt at a Planck mass relic, leaving behind a grain of gravity that never decays? Each option rewrites the finale. Each one changes what the sky would see. Human angle, a night shift at a high-altitude array. Air is thin, coffee is bad. A graduate student has a script running that flags subminute hardening events above a moving threshold. Every time it dings, her heart jumps. Mostly it's noise, cosmic rays pretending to be drama. She logs each false alarm anyway. The log is a small act of faith. Across the ocean, another team scrolls through years of data from a gamma satellite, training a classifier on known bursts to catch the misfits. They built a category called Hawking Pops. It's empty for now. Impact if one goes off nearby isn't subtle. A lunar mass black hole in its last breath would dump out a firework of particles and gamma rays that would light up wide-field instruments. Neutrino detectors might catch a whisper of the hadronic mess. If it happened within the solar neighborhood, amateur astronomers wouldn't see it with backyard telescopes, but the instruments meant for violence would. It would join the short list of signals that arrive with their own explanation baked in. But there's a switch hidden in that final instant, and it's the one people avoid naming because it turns the spectacle into a threat. High energy concentration in a small volume presses at the boundaries of our vacuum. If our vacuum is only metastable, good enough but not the best, the right kind of kick could, in principle, tip a patch into a lower energy state. In a kitchen, that's supercooled water snapping to ice when you tap the glass. In spacetime, that's a bubble of true vacuum forming and expanding at nearly light speed, rewriting physics as it goes. A PBH's last exhale, if it's hot enough and structured in the wrong way, could be that tap. Now nobody's claiming inevitability. Calculations put us uncomfortably close to the edge but not obviously over it. The Higgs potential hints, with caveats as big as galaxies. Still, the coincidence nags. End-stage temperatures in the rough ballpark, energy densities that don't happen anywhere else anymore, and a mechanism tied to horizons that couple interior and exterior states just when the fuse burns fastest. This remains firmly in theory space, plausible in models, unproven in nature. Meanwhile, even without catastrophe, the final second teaches us about horizons themselves. The information debate gets loud here. If evaporation is unitary, correlations among the outgoing quanta must crescendo at the end. That means the burst isn't random static, it's structured noise, with entanglement patterns we don't yet know how to read. The last breath could be the clearest broadcast a black hole ever sends, if anyone's listening with the right decoder. A microstory to hold onto. A theorist sits on a balcony after midnight, laptop closed, city humming below. He's been calculating gray-body factors all day, the way the hole's curved spacetime filters outgoing modes. He can't shake a simple image, a candle that burns for eons, then, in its final flicker, writes a message in smoke. Maybe it's nothing more than heat. Maybe it's the only note the universe still remembers how to sing from its childhood. We've listened for the note. So far, nothing. But instruments are sharpening, cadences are tightening. Archive searches get smarter. The final second hasn't visited our detectors yet, or if it has, we didn't recognize it. Either way, the fuse doesn't care. It burns. And if that last breath can do more than light the sky, if it can reach for the vacuum's hidden switch, then we need to talk about the vacuum we live in and why it might not be as safe as it feels. The vacuum that isn't guaranteed safe. There's a word physicists use when the floor looks solid but might not be: metastable. Good enough until it is. The stakes are simple and brutal. If our vacuum is only a temporary arrangement of fields and forces, then there exists a lower energy state, a truer vacuum waiting behind a barrier. Cross that barrier in one place and a bubble forms. The bubble doesn't drift. It sprints at near light speed, converting everything it touches to new rules. No alarm, no warning. Just a wave of different physics. Why do we even suspect this? The Higgs. When the Higgs boson showed up near 125 GeV and the top quark sat heavier than we hoped, a strange inference emerged from the math. Run the standard model backwards through energy scales and the Higgs potential. The energy landscape that tells the Higgs what value to sit at tilts ever so slightly the wrong way. Depending on inputs and how much faith you put in no new physics, our vacuum could be perched on a ledge. Not obviously doomed, not clearly safe, uncomfortably in between. Action the way the argument unfolds. You model the Higgs field's potential like a bowl with a little dimple. Our universe sits in the dimple, but there's a deeper basin far away across a barrier. Quantum mechanics allows tunneling. The field can, with unimaginably small probability, punch through and land in the deeper basin, nucleating a true vacuum bubble. The inside of that bubble has different constants and particle masses. Chemistry doesn't survive the border crossing. Neither do atoms. Neither do we. Complication 1. The numbers. In straight standard model calculations, the lifetime of our metastable vacuum dwarfs the age of the universe by absurd factors. On paper, we're fine. But that comfort comes with caveats. Add gravity corrections, high energy effects we haven't measured, or unknown heavy fields, and the tunneling rate can shift. Most shifts make us safer. Some don't. And here's where the PBH fuse intrudes. Concentrated energy can act like a seed. High-energy collisions, or a hot, tiny region driven out of equilibrium, can in principle catalyze a transition. A dying primordial black hole is very good at making hot, tiny regions. Human moment, small and honest. A physicist at her kitchen table stares at a napkin sketch of the Higgs potential, two valleys, a thin ridge. She says to her partner, "We'd never see it coming." She doesn't mean to scare anyone. She's just translating an equation into a feeling. If a bubble starts beyond our horizon, it's invisible until it's on top of us. If it starts locally, we don't get a headline. We just don't get. Meanwhile, calculations push both ways. Some argue black holes suppress false vacuum nucleation by warping spacetime, stretching the barrier, making tunneling harder. Others show that horizons can host instantaneous solutions, seeded bubbles perched near the edge that tip more easily. It depends on details, the exact Higgs top masses, higher dimensional operators, the temperature history, and whether evaporation couples to hidden sectors. The math is sharp, but the inputs blur. The result is a corridor of uncertainty, exactly where nobody wants a corridor. Impact isn't just existential, it's conceptual. If our vacuum is metastable, then the laws we recite are local customs. They hold because the field sits where it sits. A true vacuum bubble would rewrite the customs. New particle masses, altered couplings, different symmetry breaking. Gravity's behavior could shift. Inflation's fingerprints could be erased. Cosmology would reset without preserving anything that calls itself memory. On the other side, there'd be no we to compare notes. Link it back to the fuse we're tracking. A PBH's last second is a rare modern portal to early universe energy densities. The sizzling cocktail of quanta and fields in that shrinking volume could brush the Higgs field in precisely the wrong way. Not guaranteed, not even likely if you trust the safest versions of the calculation. But it's exactly the kind of spark that fits the mechanism. A local trigger in a world that otherwise only risks transitions through impossible diffuse chance. Here's the thing we keep avoiding. If a spark can flip the vacuum, who arranged the kindling? Why does the Higgs potential sit so close to the edge that we get to argue about it at all? Why do the surviving PBH masses align with energy scales tied to phase transitions in the early universe? It could be coincidence. It could be selection. We only live in vacua that support complexity, so of course we see one like this. Or it could be something with intent. We're careful with that word. Intent is a human label, but the pattern nags. The allowed PBH mass band brushes scales where sound speeds soften and density spikes during transitions. The Higgs potential's near-knife edge metastability makes our vacuum long-lived but not immortal. End-stage evaporation provides compact, energetic taps at random places and times. Add those up, and the cosmos looks like it's carrying both slow fuses and reliable matches scattered in the dark. Speculation stays in its lane, flagged, bounded by physics, not sold as fact. This is theory space, not consensus, but it reframes terror into something else. Design continuity, a plan you only glimpse when you line up the clocks with the landscape. If gardeners exist, they didn't leave letters. They left conditions. Seeds that compress information behind horizons. Fuses long enough to let complexity bloom. A vacuum that isn't absolutely safe, so restarts aren't impossible forever. It's a story you can't prove with one plot, but you can test piece by piece. To test any of it, we start with the vacuum we have. Keep pinning down the Higgs and top masses. Push for new physics or tighten the corners where it can hide. Model evaporation with more honesty near the end, include gravity's corrections, and ask how catalysis really behaves. And then, if a PBH pops and writes itself into our sky, we read it carefully, because buried in that burst could be the one detail that tells us whether the kindling was stacked on purpose. The Cosmic Gardener Hypothesis.